Hello everyone, I hope you are doing well. So in today's video, we are going to go through the part 1 of the short answer questions of the 2023 VCE chemistry exam. And so like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. Coconut oil consists almost entirely of fats and oils. The typical fatty acid composition of coconut oil is shown in this table below. Beautiful. So we have a lot of fatty acids, and yeah, we have percentages. So we can see that we have lauric acid that is the highest percentage. All right, let's look at the question. Determine the percentage of the omega-3 fatty acid typically found in coconut oil. All right, so if it's an omega-3 fatty acid, that tells us that on the third carbon, there should be a double bond there. That's what an omega-3 is. So if it said like omega-6, on the sixth carbon, there should be a double bond. So we need to check if these basically fatty acids have a omega-3 fatty acids, or on that third carbon, it has a double bond. If it does, then it is an omega-3. The way that I'll check is by looking at my data book. Let's have a look at the first caprylic acid. Isn't it in our fatty acids? Where is fatty? There it is, fatty acids. All right, let's have a look. Caprylic. It's actually not here. Capric. What about capric? Not even here. Lauric. Lauric. Yes, lauric is here. So this one's lauric, which... Let me just do another color. So this is lauric, and let's see the composition. Aha! There is no double bond. So it's a saturated fatty acid. So this one here doesn't even have. It's not even like a it doesn't even not even an omega, because it doesn't even have a double bond. So not lauric. So I'm just gonna say, not that one. Myristic. What the hell that is? Myristic is also no. You can see that there's no actual double bonds in that one too, so not that one. That's not unsaturated. Palmitic. Palmitic also has no. Stearic. Nope, does not have. Oleic. So oleic. All right, we have a double bond, but which double bond is it? So that's 1. Sorry. So that's 1 plus 7. So that's 8. It's basically a 9 over like a 9 omega 9 acid. So 1. Is it that one? Yep. So oleic. So it's that one. 1. That's 8. It's the 9th. Yeah, it's a 9th. It's not even the 3rd. And linoleic acid. Linoleic. Where is that? Linoleic, which is this one, and it has a double bond. What? Where? So 1. That's 5, and that's 6. It's omega 6, not omega 3. Also not this one. Damn. So what about the other one, like caprylic acid and capric acid? Well, it's not even in our fatty acid data book. How can we find those? Well, we can't actually do that. How? Well, I'm thinking that what is the composition of basically saturated fatty acids, basically the ones that don't even have double bonds. And if they meet this condition, then we can say that these actually are saturated, and hence they're not even omega. So, for example, what do I mean? Like caprylic acid, we're actually given the formula for the formula. So if I do an actual calculation for this, so normally a fatty acid starts with a CC here and ends up with if it is saturated, it means no double bonds. This is what the formula should be. You have all these C's, blah, 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 and then at the end, it should be a carboxylic acid. Now, what I'm going to focus is on these parts here and this part at the beginning. Because at this part here, it's just constant. If it's an actual saturated, it's just going to be C2. It's always going to have a carbon with 2 hydrogens, and that's it. So if I look at this here, minusing these two here. So wait, let's know what the formula is here. So you can see that the inside one, the actual formula is basically when you have 1 carbon, you always have to have 2 hydrogens. That is the formula. So in other words, we can say H2N, sorry. H2N. So that's our basic formula. And so if I'm looking at this here, let's check if it fits that condition. So first, get rid of these two here. So we need to get rid of the 2 carbons, you can see. Get rid of 2 carbons. So it's going to be C6. And we have to also get rid of, so there's 3 hydrogens and 1 here, so 4 hydrogens, which basically leaves us with 12. And we get rid of those 2 oxygens. So we're basically left out with this. This here is the leftover part here. Does it fit this formula? Yes, it does. So when N is 6, hydrogens 2 times that, which is 12. Yes, it does. So it means that it doesn't even have a double bond. And if it doesn't even have a double bond, it's not even an omega acid. So straight away, this one also. And we're going to do that with capric acid too. So the same thing. So what we're going to do, what I'm going to do is the same thing. So remember, get rid of these 2 hydrogens, carbon, sorry. So it'll be basically a C8. How many hydrogens should we get rid of? 4. So 3 here and 1 here. 16. And oxygens, get the oxygens out. Okay, this one follows the same pattern. So when N is equal to 8, you double it, and it's 16. So it also is a saturated. It doesn't even have double bonds, so it cannot even be an omega-3. So overall, this whole, coconut oil does not even have any, omega-6, omega-3. So it's a 0%. 0%. State why coconut oil is resistant to oxidative rancidity. Absolutely, this is easy. Remember, oxidative rancidity only occurs, it only occurs when there is double bonds. When there is C to C double bonds, it wants to basically, when oxygen reacts, because oxygen is very reactive to those double bonds, it wants to react. And so when it reacts, it basically forms ketones and aldehydes, which gives that smelly, that musty smell, which is oxidative rancidity. But because this composition doesn't even have any carbon-to-carbon double bonds, there is no way it's going to even go through oxidative rancidity. There are ways, of course, but in terms of the study design, there's no carbon-to-carbon double bonds, which is great. So that's why it doesn't go through oxidative rancidity and it's resistant. So what we're going to say? So, coconut. Oh my God. So coconut oil has no carbon-to-carbon bonds, hence basically oxygen is what actually reacts with them and causes that oxidative rancidity. Hence oxygen can't react, which basically no oxidative rancidity. Because there's only one mark, so oxidative rancidity. Beautiful. Nice question. Next question. Coconut oil reacts in the body to produce fatty acids. Absolutely. Name the other products of this reaction. Beautiful. So remember, coconut oil is fats and oils, which are called triglycerides. So basically what it's saying is if you have a triglyceride, I don't even know how to spell it, it's something like this. We know when triglycerides, basically, when coconut oil reacts in the body to produce fatty acids. So if it's producing fatty acids, it's basically hydrolyzed. So triglycerides are getting hydrolyzed. With basically, to get triglyceride broken down, you need 3 waters. And that results in, basically, your 3 fatty acids and your glycerol backbone. So, name the other product of this reaction. It is glycerol. So we already know our 3 fatty acids. So the other one is glycerol. Beautiful. Coconut oil can be metabolized by the body to produce caprylic acid, which is this one, I think. Yep, it's this first one. Write the molecular formula of the molecule found in coconut oil that can be metabolized means broken down, to produce these 3 caprylic acid molecules. Wow. So basically they're telling us to write the molecular formula of the triglyceride. Remember, the triglyceride has both the what we call the glycerol backbone and those 3 fatty acids, which are both caprylic acids. And so that's what we want to basically write, the molecular formula for a triglyceride. Now let's do it. This is a little bit hard for a 1 marker because it does take some time. Let's think about it. All right. Okay, so we know a triglyceride basically starts with the backbone. Let me draw it a little bit thinner so you can. Let's draw it. I think we'll do 3. So there. Yeah, we'll do a 3. Why not? So 3. So we have 1, 2, 3. So it has with of course the glycerol backbone. And then we have the ester group, which is COO here, COO here, COO here, and then you have basically that fatty acid. Remember, be careful. Writing the fatty acid might be difficult because remember, you're already taking care of these here. You've already got those 2 oxygens. So, for example, this caprylic acid, these 2 oxygens are already here. They're already here. Those 2 oxygens are already here. And that extra hydrogen, you would basically that extra hydrogen. So you're basically left with, and also that extra carbon. You know this carbon? This is from the fatty acid. So basically that's going to be basically like C7, because one of the carbon's already written here. It's already here, and that's 2 oxygens and 1 hydrogen. So basically you get C7H15 oxygen. Sorry, not oxygen. You get rid of those oxygens. Yep. So that makes sense. So C75H15. Because you've already got the 2 oxygens here, 1 carbon, so you need to take it out. And the extra hydrogen would have been taken out with the water. And so, yeah, so C7H15. So C7H15, and for all of this is C7H15, C7H15. These is what your triglyceride will look. So we just want to basically write the molecular formula. So how many carbons? So how many carbons are we looking at here? So we have 1, 2, 3, 4, 5, 6. We have 6. Then 7, 14, 21. 7, 14, 21 plus 21. We basically get 27. 27. I just want to be careful with that. So 3, 6. We have 6. Yep. 7, 14, 21. Beautiful. Which is 27. And how many hydrogens? So for hydrogens, we have 1, 2, 3, 4, 5. We have 5 plus basically 15. 30, 45, which is 50 basically. We have 50. And how many oxygens? There is only 1, 2, 3, 4, 5, 6. We have 6 oxygens. That is it. That is our triglyceride formula. Absolutely. Looks good. I hope I haven't made any mistakes. Yeah, that looks good. So 2750.06. Next question. Coconut oil contains vitamin E and negligible quantities of other vitamins and minerals. The structure of vitamin E is given below. Explain why vitamin E is soluble in coconut oil. Ooh, let's have a look at it. So we can see that we have this long non-polar part here. It doesn't even have any oxygen, so we can't. And then we also have this non-polar part here. Of course, those non-polar, but we only have these extra that create polar. But overall, the vitamin E molecule is all made out of, it's largely non-polar, we can see. And so, if it is soluble in coconut oil, it means coconut oil has to be non-polar if they are soluble. So let's check why it's this one soluble. Absolutely, this is soluble too. You can see that. Yes, we have oxygens, but we have so much amount of those carbons. It's a very long fatty acids. Remember, you have fatty acid tails. Those fatty acid tails are very long in terms of, they basically make the whole molecule non-polar. So we basically have, because we have non-polar and non-polar, you remember, they basically are soluble with each other. So, looking at this here, explain why vitamin E is soluble in coconut oil, and it's 2 marks. So we're just going to basically say vitamin E and coconut oil are both non-polar. That should explain one of them. We need to say because of what. So vitamin. I don't like that. So let me just make it bigger. Okay. So vitamin E and coconut oil are both non-polar. So that should give you 1 mark, saying that they're both non-polar. And then we have to talk about their interactions. They're actually intermolecular forces. Because they are both non-polar, they're going to basically, hence, they will basically create dispersion forces around them, and hence, between these two. So dispersion forces will be formed between those 2 compounds. That's what is going to make them soluble, basically. Hence, dispersion forces will be formed between the 2 compounds. Beautiful. Scientists are investigating the possibility of using coconut oil with the aqueous electrolyte potassium hydroxide to power a fuel cell. Write the half equation that would occur at the cathode of a coconut fuel cell in an alkaline electrolyte. Well, let's just draw a basic fuel cell here. If this was the fuel cell, what do we know about a fuel cell? Let's draw a nice fuel cell here. So it's like a box. And say it like this. Okay, of course we have those two electrodes here. Now we know the electrolyte here is, potassium hydroxide, which is basically very basic, and it has OH ions, OH minus ions. So it's actually alkaline. And remember this, always remember. This is what you need to remember. Your fuel is always going to, in a fuel cell, your fuel is always at the anode, which is basically negative. Your cathode is basically where oxygen goes to. So basically, this is where your fuel is going to be entering. Remember, fuel always enters through the anode in a fuel cell, and the cathode is basically what you'll give it with, which is basically normally oxygen. So you react oxygen with most of these. So your cathode is where you basically input your oxygen. Yeah, so this is like a very nice basic written fuel cell. So if you want to write the half equation that would occur at the cathode of the coconut oil in an alkaline electrolyte, this is what we want to know. We want to see oxygen reacting with OH in an alkaline environment. So this is very easy because it's actually in your data book. So let's have a look at where oxygen is reacting. Look at our data book. Where does oxygen react? Oxygen. We got oxygen here, 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 and that is it. Now let's look at which one is right. It cannot be this one because it has, it's not alkaline, it's basically acidic because of the H plus ion, so not that one. Also the same as with this one, so take that out. And you're left out with this one. Yes, it is alkaline. You can see that OH minus ions, beautiful. And hence, because it is, it's a cathode and where reduction occurs, it's going to basically be this reaction here going forwards. So, rewrite the whole equation. So, write what you just saw. O2, gas, plus 2H2O, liquid, 4 electrons, goes to 4OH minus, AQS. Beautiful. That looks perfect. Done. Let's go down back here. All right. Let me just make this small now. All right. So, stay one design feature of the cathode that helps the fuel cell operate efficiently. So, there's actually many ways, like many things you can talk about the cathode. You can say the first thing that comes to my mind when you're looking at the electrodes in a fuel cell, especially like cathode and anode, they are porous. Basically, they have little holes, which basically increases the surface area. So, better gas exchange basically, and hence if there is high surface area, there has to be a faster rate of reaction because it increases. Remember, high surface area means faster rate of reaction. That's what one of the designs. There's so much more you can talk about. You could talk about basically you need a constant supply of reactants. Yeah, there's like a lot. But the first thing that comes to my mind is porous. So that's what I'm going to write. So it is porous. So let me just do another color. So because it's 1 mark, we're just going to go very basic. So yes, which results high surface area. It's in high surface area. Hence, fast rate of reaction. Rate of reaction. Beautiful, nice. Question G. State one reason why it may be better to obtain energy from a coconut oil using a fuel cell rather than direct combustion. Oh my god, this is fun and easy. Remember, fuel cells are very, very efficient. They're approximately, from what I believe, it's like they're 80% efficient. Basically, their main source, their main energy conversion is basically chemical to electrical. And whereas, of course, you have some thermal, but that's 10-15%, but most of it's so efficient that it's its main source, what's main energy conversion is basically from chemical to electrical, and hence creates good electricity. So not a lot of wastage in terms of energy. Whereas direct combustion is a big problem. Direct combustion has so many energy losses because it has so many energy conversions. Let me explain. So basically in direct combustion, what happens is basically you take those coals or those chemical energy and you basically combust them. And so when you combust them, thermal energy will be produced. And so that thermal energy is basically taken and it's being used to move a turbine. So we went from basically chemical to thermal and to mechanical, moving that turbine. And so that turbine moves a generator which generates electricity. Now, that is for energy conversions. Now, remember, there's going to be energy wastages. Like, for example, say the generator, the turbine, it's of course, there's friction into it, and hence some energy has to be going above the, friction to make it move. And so that takes some energy. So it is one of the most, in comparison to the fuel cell, absolutely, direct combustion is it's so inefficient because it has a lot of energy conversions and hence results in such energy losses. And yeah, basically because it's 1 mark, you just talk about how it's not efficient. Let's do that. So G, we'll say fuel cells are more efficient than direct combustion, as direct combustion has many energy conversions which result in energy losses, loss. Beautiful. Give one reason why coconut oil may not be practical fuel cell for a fuel cell. So wait, not be a practical fuel for a fuel cell. Do not refer to the environmental issues or sustainability in your answer, Dame. So give one reason why coconut oil may not be practical for a fuel cell. There's so many answers you can talk about it. Can we wait? So because I know for a fact that I'm trying to think, like, how we know about this coconut oil? We know that there's no double bonds. Does that help us with anything? Like, can we say something? Because there's so many things that we can say. Nah, I don't think you can say anything about the double bonds. What can we say? All right, no, I think we can say something. All right. So basically, coconut oil is actually partially oxidized. What do we mean by partially oxidized? Can you see how there's a lot of oxygens? You see all these little oxygens here? Basically, look, when you're doing a combustion reaction, with a fuel, you're reacting with oxygen gas. So basically, you're reacting with oxygen gas, and hence it basically, releases water. So basically, when we're oxidizing the fuel, we're actually oxidizing the fuel. And so when the fuel, it doesn't have a lot of oxygens. So when a fuel has like some oxygens, it means it's already been partially oxidized, which means its energy content is very low. So, for example, a fuel that has no oxygens and you basically react with oxygen, it's going to react very violently because it has a lot of energy, which is great. But because, the coconut oil already has a lot of oxygen, it means that it's already been a little bit partially oxidized. So when you're actually reacting it, it's not going to give us a lot of energy. So it will produce less energy, which is actually not very good enough. So it's not sufficient enough for especially a fuel cell. I think that's the first thing that's coming to my mind. Yeah, there's so much more I think you could talk about. My brain's not working, so I think that's the most easiest, I would say. How there's a lot of oxygens. We can see that there's a lot of oxygens. Remember, the more oxygens that you have, the more it's partially oxidized, and hence the fuel is it doesn't produce a lot of energy. And so that is a very hint. Don't always when there's questions like this, make sure to remember, if you see a lot of oxygens, it's partially oxidized. So that's what I'm going to basically say. All right, and it's not practical, of course, because it has a low energy density and hence produces less energy. So yeah. Coconut oil is already partially oxidized, as it basically contains many oxygens. Thus, coconut oil will have a low energy density. So a low energy density. So density, and will produce less energy, and will produce less energy. Beautiful. I hope that kind of answers that question. Question 2. Beautiful. Let's move on to the next question. Let's have a look at this. Cow's milk contains proteins, fats, carbohydrates. The main carbohydrate in cow's milk is lactose, of course. So the reaction for the breakdown of lactose is catalyzed by an enzyme called lactase, and shown below. Okay, we have alpha lactose, and it's broken down, and we get this. All right. A linkage has been circled with a dashed line in the lactose molecule shown above. Name the circle linkage. Beautiful. This is called a glycosidic linkage. A glycosidic linkage. Linkage. Beautiful. Explain what the GI of a food indicates. Remember, what is GI? I mean, it's not anymore in the study design, so you don't have to know it for the next students in 2024. But GI stands for glycemic. I can't even say glycemic index. It basically like refers to how fast is the food being hydrolyzed into glucose. Sorry. So how fast is food? The carbohydrates they eat, basically hydrolyzed into the basic unit of glucose. And so basically, if it goes quickly, like if the glycemic index is very high for some certain foods, like for example, when you eat like a lolly, if it has a high glycemic index, it basically means that the food gets very hydrolyzed very quickly into glucose molecules, and hence your blood sugar levels go up. So basically, glycemic index, what it does overall is measures glucose on blood sugar levels and how fast overall, basically glucose gets hydrolyzed. So foods get hydrolyzed into glucose molecules. And that's what it basically measures. So it basically measures the blood sugar levels of glucose and how fast it basically, the body basically breaks down food to glucose. Easy. So for 2 marks, that's what we're going to say. Glycemic index, which GI refers to how quickly food gets hydrolyzed. So hydrolyzed like that, hydrolyzed into glucose. Hence, it allows us to measure glucose on blood. So glucose on blood sugar levels. Beautiful. State why the breakdown of lactose as shown above contributes to the GI of lactose. So GI, your glycemic index. Why does it do? Well, makes sense, because if you're breaking down lactose using a reactant, basically you're using a reactant X and you're basically breaking down lactose, of course, you're breaking it down into glucose molecules. You can see that you've been breaking it, they're not, of course, one's glucose and one's something else, but if you're breaking it down into glucose, your glycemic index is going to go up because now there's, in your blood, sugar levels have glucose in them. So that's why, overall, what did it say? The question is, sorry? State why the breakdown of lactose as shown contributes to the GI, because when you're hydrolyzing it, you're producing glucose and hence your GI increases. Very, very nice and easy. So let's write that down. When lactose is hydrolyzed, glucose is produced. Hence, GI basically increases. Done. Proline is found in both in cow's milk and in the enzyme lactase. Proline is a non-essential amino acid. The structure of proline is shown in the data book. State why proline is not an essential amino acid. Basically, non-essential amino acids means that you don't need to consume it in a diet because your body overall synthesizes it by itself or creates it by its own self. You actually don't need it, need to consume it. So that's what basically non-essential amino acids are. So basically means that it can be synthesized by the body and does not need to be consumed. So it does not need to be consumed in a diet. Beautiful. Draw the structure of proline as it would be in an acidic solution. Whoa, well, let's have a try at that. So let's have a draw at proline. So I'm going to use a different color. So where's proline? It's an amino acid. So let's go down to our amino acid. Proline, where are you? There it is. Proline is here. So proline, this is the structure of proline. Let's have a sketch at it. So basically, I wish I can just kind of, I'm just going to draw this on it, and I'm going to copy and paste it. So it's like a nice structure, you can see it. Just like that. Like this, okay. Copy, paste. There it is. So, okay. Let me make this bigger. Okay. So, what do we have? Of course, we have the COOH here, and we have the NH group. All right. That's what proline basically looks like. Now, in an acidic solution, imagine you have an acidic solution. So basically it's an acid. We know acidic solution. So imagine the environment is filled with acidic solution, meaning that it has a lot of H plus ions. And so basically because it is very acidic, it means this is going to act as our acid. Your environment, your H pluses are going to act as our acid, and hence that proline is going to act as a base. And remember what an acid does, it basically donates protons, whereas a base accepts them. So this is going to donate it, and it's going to donate it to the NH. NH, so it's going to basically be a positively charged NH2, basically, yeah. It's going to have a extra hydrogen now, and it's going to be NH2, and it's going to have a positively charged. Beautiful. That's what's going to happen. A very easy, nice question. So total structural component as it would be in an acidic solution. Done. So I have a positively charged. Next question. Proline is found in proteins throughout the human body. Identify 2 types of enzyme catalyzed chemical reactions involving proline in the human body. So 2 enzyme catalyzed chemical reactions involving proline in the human body. Easy. So one of the most 2 things that come up is basically like hydrolysis. That's a reaction because when you have, let's say you're eating a protein, like an actual protein, chicken or something you're eating, what's going to happen? Your body's going to break it down into its amino acids, and hence you form protein. You form proline. So basically a kind of a type of a reaction that involves proline in the body is basically hydrolysis of protein, which basically so the protein contains proline. And so basically when you hydrolyze it, you break it down into proline itself. So let's write that down. Hydrolysis of protein. Which has proline. So basically when you hydrolyze hydrolysis of protein which has proline into basically proline. So you're basically breaking it down to proline. Another one is basically the condensation reaction. So when you actually have in your body proline and you want to form, what do we call them? What do I say? So when you want to basically form proteins, your body needs, so it's when it's broken down into amino acids like the proline, your body uses condensation reactions to form proteins. And that's another one that kind of involves proline. So you'd say condensation reaction using proline to form proteins. Done. Explain why proline has 2 optical isomers. Beautiful, easy question. Now, there's actually a formula for this. Optical isomers. How can you determine how many optical isomers there are? It depends on this rule. 2 to the power of n. It's actually a rule where n is the number of chiral carbons in a compound. Where, example, in this is we want to determine the optical isomers in proline. So proline, let's have a look at proline structure. Sorry, not this one, because this one's all kind of affected. So let's go back to its original. Have a look at this proline here. Remember, what is a chiral carbon? It basically just has, it has 4 different groups around it, attached to it. So, and overall, what does optical isomers have? In other words, they're called enantiomers. And basically, their mirror images cannot be superimposed with each other. They cannot be put on top of each other. And so, which of these carbons, how many carbons are there that are chiral? You got one right over here. You see this one here? That's one. And basically, there's nothing else. I mean, like, from what I'm looking here, there's none. It's only this part here because we have this side, and we have a H plus here. So totally different. So we only have one. So putting it in our formula, 2 to the power of 1, which is just 2. So You only get 2 optical isomers. Now, can I be honest with you? I don't think they'll accept using the formula. Now, I'm still going to put it. It is a very quick way that you can kind of get answers, I'm not going to lie. Like, to get the answers, but I'm going to still write it. So what I'm going to get those 2 marks, this is what I think you should write. You need to say how many carbons there are, because that's what basically determines the optical isomers. So we know that there's 1 carbon, and hence I'm probably going to just say, using the 2 to the power n rule, this results in 2 optical isomers. And I don't think that'll still be enough for the 2 marks. I think the 1 mark comes from the chiral. Then maybe just talk about like how to be a chiral carbon, you have to have 4 different groups, and hence the mirror images cannot be superimposed. That's what I'm basically going to write. Yeah, because it's 2 marks, and I don't think they'll accept the 2 to the power n rule. So, but yeah, do that 2 to the power n rule is very, very useful. Determine how many. So, we can say it basically contains 1 chiral carbon using, we said, 2 to the power n rule. This results in 2 optical isomers. So in 2 optical isomers, and yeah, so we sound like chiral carbons have 4 different groups attached to it. So groups attached to it. This means the mirror images cannot be superimposed, cannot be superimposed. And I think that was enough, I'll be honest. Next question, this is the last one. Yep, for question 2. Only one of the proline optical isomers is found in lactase. Explain why lactase must contain the correct optical isomer of proline to function as an enzyme in the digestion of calcium milk. Absolutely. I think it's one of the most I think they've made a big mistake, a lot of students. You need to remember, if there's 2 optical isomers, one's going to be correct. And sometimes the other one's always a bad optical isomer. So it's very important to have the right optical isomer. And why? Why is that? Let's think about it. Now, remember, enzymes are basically created by a folding of protein chains. Remember, enzymes, there's a lot of amino acids in a chain, and hence they form proteins. And it's basically when these proteins fold, and so they form hydrogen bonding and all that stuff. And basically, this is what creates an enzyme. An enzyme is a 3-dimensional structure. And so basically what it has is, because of that protein chain, remember that protein chain has proline, the correct proline. Let's say it has the correct proline. What it will do is it will form the right active site. It creates the perfect structure of the active site that basically binds to that lactose, that substrate, which is our lactose in this case. So overall, there's actually a specific amino acid sequence that includes proline. Therefore, that determines the shape and the active site. And so having the wrong proline, having the other optical isomer of proline, basically, you might think, okay, they have the same molecular formula and all that stuff, but you got to remember they have different the rearrangements. The spatial rearrangement are totally different, meaning they actually affect the active site shape. That proline is totally different. It actually, affects the active site shape, hence basically making lactose, the substrate, not even bind to that active site of the enzyme. And hence not they're basically making the enzyme very ineffective, not even useful, to be honest. So lactose won't actually be, broken down. It won't be actually digested. And so that's why it's very, very important to have the correct orientation of proline, that optical isomer, the correct one. Because it makes the actual enzyme's active site proper. It makes it the proper one. And so hence, when lactose basically binds to it, it breaks down to lactose. So it is very, very kind of important to know, there has to be, to not make a mistake on the wrong optical isomers, because it does really affect it. Now, it is 2 marks. Now, I've said a lot of stuff, to be honest. Wow, explain why lactose must contain the correct optical isomer of proline as an enzyme in digestion in the cow's milk. All right, let's just say what we said. So what we're going to say, what should you say? Because it's like a little bit big, this one. What do we say? Okay, we're gonna say enzymes. Sorry, I'm gonna write a lot just to be kind of. I know it's more than a lot. I'm gonna try to write a lot so you can when you guys read it, you can be like, oh, that's how you do it. Okay, that's what it means. Yeah, because I think when I'm saying it, I think it's a little bit confusing. But yeah, so I'm gonna say okay. So we said basically enzymes. You know, enzymes we know have specific, three-dimensional. Oh my god! What's with me? Dimensional structure that is formed by the folding. Remember those protein chains, those amino acid chains. Basically, what happens is when they fold, they create our three-dimensional structure, our tertiary structure. That is formed of the protein chain. This structure creates an active site where the substrate, which is basically in this case lactose. So remember, the substrate is our lactose, binds. So yep. So enzymes have specific three-dimensional structure, and that is formed from the protein chain. This structure creates an active site where the substrate binds. So basically, the specific arrangement of amino acids. So arrangement of amino acids. Including basically like the proline, that's the most important one, including proline, determines the shape and function of the active site. That's why it's very important. Function of the active site. So if you basically have so we wrote that, and we're going to talk about what happens when you have an incorrect. So an incorrect proline proline isomer will alter the active site. Active site function or shape. Basically, you can alter every function or shape, potentially causing like a mismatch, causing a mismatch with lactose, making the enzyme ineffective basically. Beautiful. So an incorrect proline isomer will alter the active site, function or shape, potentially causing a mismatch with lactose, making the enzyme basically ineffective. And so that's why you need to basically have the correct isomer. So I think we'll just talk about the correct isomer. I think I'm just talking too much, but I'm trying to be kind of very using the correct isomer. So using the correct isomer, we'll have the right orientation. We'll have the right orientation, allowing lactose to bind properly to the active site, And so hence basically breaks down, the lactose breaks down. I think it's a lot for 2 marker, but I hope that makes sense, like kind of very in detail. But yeah, let's move on to the next question 3. Let's do this. Propane is used as a fuel for barbecues. Calculate the amount of energy released when 140 grams of propane is completely combusted. Easy. if we have, so energy is basically, if we have 140 grams, we multiply it by, let's go to our formula sheet, propane. Let's look at where they are. There it is. So propane is this. So basically it produces, for every gram, it produces 50.5 kilojoules. So we have 140 grams, we multiply it by that. There it is. Okay, so that's going to give me, what? 140 times 50.5. That gives me basically just 3 significant figures. 7.07 times 10 to the power. So 1, 2, 3. 3 kilojoules. Beautiful. Beautiful, done. Write a thermochemical equation for the complete combustion of propane at CLC, so standard laboratory conditions. Let's do that. So propane, which is basically C3H8, and in CLC it's basically gaseous. So 3, I don't want to see him say. Okay, beautiful. We know oxygen is gaseous too in CLC. Water is in liquid at CLC. Remember, a standard laboratory is actually liquid, and CO2 is also gaseous. We have 3 carbons here, so 3 carbons. How many hydrogens? We have 8 here, so we have to have 4 here. So how many oxygens here now? So we have 4 plus 6, which is 10. So if I put a 5 here, we get 10. Beautiful, done. Not actually done, because we still have to get our, it's a thermochemical equation. We need to have our enthalpy change. So enthalpy change, of course, it's a combustion, so it has to be negative what? So it's in your formula sheet. Because we're only getting, basically you can see that it is 1 mole of propane. So that is what? 1 mole of propane gives you this. 2,220 kilojoules per mole. Done. All right, that's it. Next question. Sketch the energy profile for the complete combustion of propane on the axis below. Beautiful. It's only 1 mark, so just the energy profile. Like, we know it's combustion reaction, so it's going to go like high reactants, and so it's going to go down. So we have a negative enthalpy change like that. There it is. You just move like that. Beautiful. That is, I mean, that's all you need. So it's just sketch the energy profile. You don't need to like label. Yeah. State how the energy profile for the incomplete combustion of propane would differ from the diagram you've drawn. So the one that we drew was an actual complete combustion. Remember, what is incomplete combustion? Like, what is it? Basically, what incomplete combustion is basically where you have limited oxygen supply. So you basically don't fully oxidize propane. Like, if you basically, let's have a look at here. So basically, if you basically have an incomplete combustion, you don't release as much energy. Remember, have you ever seen in exam questions where basically if you have like, this is the complete combustion of propane, this is the energy that's going to be released. But if you actually look at the same propane, but in an incomplete combustion, you're going to see that this here is less because we're releasing less energy. Because why? Because propane it's like partially oxidized. It's not fully oxidized because we only have limited supply of oxygen. That's why it basically is an incomplete combustion. Hence, not all energy is going to be released out of that propane, and hence your enthalpy change should be smaller than a complete combustion. So let's have a try to sketch at it. So imagine, think of it like this. If you think of it like this, so imagine we start at the same reactant energy, but let's say we have the same activation energy, and it goes down. Because the enthalpy change is less, it has to end somewhere here, around here. Can you see how the enthalpy is less than the your complete combustion? Of course, because we're releasing less energy. So it means what? What is the overall thing? You can see that the actual energies of the products is actually greater than the energies of the complete combustion. That's the big difference between them. So let's take that. Kind of. Okay, wow, I don't know why that... Okay, let's just draw it nicely again. But yeah, so overall... There it is. So overall, let's write that. So we're going to say incomplete combustion. So incomplete combustion result in partial oxidation. Of propane. Hence, not all energy is released, and change in H. Your change in H is will be basically smaller. Basically, the final enthalpy also, the final enthalpy we saw, so the final enthalpy of the product, so the energy of the product, is greater. Will be higher, I would say, will be higher when we looked at it in our diagram. Beautiful. Question B. An equation for the complete combustion of ethanol is shown. Okay, we got that. 96 grams of ethanol completely combusts and the CO2 produced is collected. Calculate the volume of a tank required to store the captured CO2 at 15 degrees Celsius and 100 kilopascals. Easy. So, let's determine the number of moles of ethanol. So, C2H5OH, which is basically remember, it's mass over molar mass. So, what's the mass of ethanol? It's 96 over molar mass. So what's the molar mass of ethanol? So let's try to do that. We have 2 carbons. So we have two carbons. Oops, what's that mean? So we have 2 carbons plus 1 oxygen, so 16, plus we have 6 hydrogens. We get 46 basically. 46, so that is going to give me 96 over that. I get 2.08, basically around moles of ethanol. And so doing ratios, we should get how many CO2. So CO2, the number of moles of CO2 is basically 2.08 times. So the ratio is 2 to 1, so 2 over 1. So basically 2 over 1 is just 2. So times that by 2, you get 4.178, like 9 mole, but so 173 mole. And so now using PV and RT, so the pressure is what? 100. V is your volume, which we're trying to calculate. N is basically 4.173. R is 8.31. T is the temperature in Kelvin. So 15 plus 273 to get it in Kelvin. And so basically your volume is, so basically 8.31 times 15 plus 273. Basically that gives me 19, how many second figures? 3, so 99.9 liters. We're going to need, the volume of the tank should be 99.9 liters. Easy. The molar mass of ethanol is 46 grams per mole, and the molar mass of propane is this. State whether the flashpoint of ethanol is higher or lower than the flashpoint of propane. Explain the reasons for your choice with reference to the structure of both molecules. All right, let's have a sketch at ethanol. Ethanol basically looks like CCOH. We have all hydrogens here. All right, and what was the next one? Propane, just CCC. Okay, let's have a look at this. Remember, your flashpoint increases if your intermolecular forces, so the higher into your molecular forces, the higher the flashpoint. And remember, your flashpoint is like the lowest temperature at which vapor is basically released. So something like a fuel that has a very low flashpoint means it's very flammable. The higher the flashpoint means the more energy that you need to do to break those bonds and hence let it to burn it or to ignite it. So having a look at this, what do we see? Well, we see ethanol can have basically dispersion forces, can form dispersion forces, and hydrogen bonding because of that oxygen, that hydroxyl group. Hydrogen bonding. This one over here only has dispersion forces. So the one that actually has the stronger intermolecular forces is actually ethanol. So overall, ethanols will have a higher flashpoint than propane. And remember, the second mark basically would come by just saying because ethanol has, hydrogen bonding and dispersion forces, while propane just only has dispersion forces. And and remember, because ethanol has a stronger intermolecular forces, remember, because it has those strong intermolecular forces, it will produce less vapor. And that's because you need to put more energy to break those intermolecular forces and hence basically ignite it. And yeah, so that's what we're basically going to write about. So let's do that. So the first one is basically the flash point of ethanol will be higher than propane. Ethanol forms hydrogen bonding. So hydrogen bonds due to the hydroxyl, hydroxyl group, and dispersion forces. Whereas propane only forms dispersion forces. Beautiful. So dispersion forces. Hence, ethanol has stronger intermolecular bonds and will produce less vapor, as ethanol is harder to ignite, so as there is less vapor and harder to ignite. Ethanol is harder to ignite as it requires, do we say everything? The partial will be ethanol. Ethanol forms hydrogen bonds due to hydrogen bonds and dispersion force, whereas propane exists. Hence, ethanol has a stronger intermolecular force and will produce less vapor as ethanol is harder to ignite, as it needs high energy, basically high energy to break the intermolecular forces. The intermolecular forces. That is it. Beautiful. Question 4. Let's have a try at this. So, question 4 states, the diagram below shows the reaction pathway starting with butane 1-ene. So I'm going to just draw the structure. Whenever you're starting these questions, like I've seen these questions, these are like your synthesis. Always draw the structure. So butane 1-ene. So C. So at 1, so there's going to be a double bond here. And yeah, this is what butane 1-ene looks like. With a hydrogen here. This is what it looks like. All right. Done. So butane 1-ene can react with water at 300 degrees Celsius with, this act as a catalyst to produce two different products, compound Q and compound R. Only compound R can react to produce butanoic acid. Name the type of reaction that forms compound Q and compound R from butane 1-ene. So we're reacting it with water. Look at that, water. So when you're reacting this with water, what's going to happen? So this is an addition reaction because we're going to get two possible results here. Remember, you can get, when you basically form this, you can actually get two structures. You can get that OH, the alcohol group here, because of the water, so that OH can be hitting it here. So basically you should get something like this then. You'll form something like this, so basically this over here. Or it could actually hit here, this carbon over here, the OH. So it would look like this basically. Beautiful. So these are the basically two possibilities of what you could get reacting it. So let me kind of write that nicely. So you got basically this one over here, and you got a possibility it could have been here. So that OH could have went through this carbon, or it could have went through this carbon through that double bond. So you get two possibilities, of course. Now, what we want to do is basically name the type of reaction that involves that forms compound Q and compound R to form butane 1-ene. Beautiful. So when you're forming and you're reacting with H2O, remember that H2O here? What is it? It's an addition reaction, because what it's happened is everything is being used to being added to this. For example, that oxygen is basically, for example, let's look at it here. That oxygen is here now. One of the hydrogens is here, and the extra hydrogen is used here. And so we basically form this. So everything's basically added. So it is an addition reaction. Beautiful. So this is called an addition reaction. So addition reaction. Give the IUPAC name of the compound Q in the box provided in the diagram above. All right, so compound Q. So, okay, so compound out in the long term forms butanoic acid. And now remember, butanoic acid can only be formed by this here. Why? Because it is a primary alcohol. So when you're actually reacting with this, you will actually, this becomes acidic, and it's at the end. Can you see how it's a primary alcohol? Meaning that, looking at this carbon here, it only has one alkyl group here. Whereas this one over here, this carbon here, where it's the O is basically bonded, has these two here. So it's a secondary, and it's basically secondary alcohol. So secondary alcohols only form ketones, or they form ketones, whereas these one here, primary, tend to form, looking at my here, if you don't know, this is the best diagram that I have on my data book. You should memorize this. So this one here, here it is. Basically here it is. We have this alcohol, and basically, because it's a first degree, we call it first degree or primary, it can basically go through making a carboxylic acid, or it can go forming an aldehyde. Whereas the one that we basically have here can only form a ketone. So that is it. So the one that actually is in compound Q in the way, so it's actually this one over here. The basically, not the ketone, what am I saying? It's basically this one here, this alcohol here, which is what? Do we have to get IUPAC name? Okay, the IUPAC name in the provided diagram below. All right, so basically what it is, it's 1 2 3 4, it's 4, so it's butane. So butane, not butane, but butane what? So 1 2, so butane 2 all, because the oxygen, so OH, is at the second carbon. You can see that. So 1 2 here. So butane 2 all, done. Next question. As shown in the diagram, compound A can oxidize completely in acidified potassium dichromate solution. Yes, to form butanoic acid. Yes, true. And yep, it's shown here. So compound R can also undergo incomplete oxidation to form compound T. Draw the structural formula of compound T in the space below. All right, easy. So basically this here, your alcohol can, remember how we said, because it's a primary alcohol, it can go through two reactions. It can make that carboxylic acid, which we just got, or it could have formed an aldehyde here. There's an aldehyde group. So that's what it is. That's what your compound T is. So let's have a sketch at it here. So basically, it's going to be those 4 C's, was it? Here. It's going to be 4 C's, 1 2 3, yep. And it's going to be an aldehyde group. So it's going to have a double O here, and H, and these are all formed. Done. Nice and easy. So make sure you have this memorized. It's one of the best tables. Done. Okay. Under certain conditions, butanoic acid reacts with ethane amine. Let's have a look at this. Okay, you can see that. Yeah. Under certain conditions, butanoic acid reacts with ethane amine to produce compound S. Draw the skeletal structure of compound S in the box provided in the diagram at page 20. So compound S. All right, let's think about it. So we're reacting what? Butanoic acid. So let's draw butanoic. So CC, which looks like this. We have butanoic acid here, and we're basically reacting it with ethane amine. So basically ethane amine looks like this, so 2 C's, and has an amine group. Let's draw it the opposite way so we can, because I can see that it is what? Yes. So CC. This here is an amide group. Basically what they're going to react is basically they're going to get rid of a water molecule. So they're basically going to condensate. It's going to be a condensation reaction. So they get rid of a molecule. And so think of it as like two amino acids basically forming each other. They form an amide group. And so like a polypeptide linkage. That's what it is. So then we get CCC, double O here. N, of course a H here. Don't forget that H. CC. Done. So that is it. That's what it will form. And so we just need to draw the skeletal formula for this. Okay. I want to get rid of this. Why can I not get that? I want to get rid of this. Normally it says delete. I'm going to say car. Okay. So if I want to draw a skeletal, how many carbons? So we have 1, 2, and 3. Sorry, wasn't it 4? Am I fully... There's 4. Yeah, there is 4. What am I doing? It's butanoic acid, butane. So C, this 3. Yep, C. Yep, butanoic acid. Yep. So we have those 4 plus N, which is ethane. Yep, absolutely. Okay, so if we're drawing a skeletal formula, how many? So we have 1, 2, 3, 4. So 1, 2, 3. Draw it nicer. 1, 2, 3, 4. And on the 4th carbon, it has a double oxygen. So double O. And then it forms, basically gets bonded to a nitrogen. So let me nicely put these together. And basically gets bonded to a nitrogen that has a H. Now remember, if you just write nitrogen, they'll think that you've took the H out. So put the H in there. And then we also have, again, 1 and then 2. So these 2 extra carbons here. Does that look right? So 1, 2, 3, 4. 1, 2, 3, 4. Okay, yep. Beautiful. That looks correct. So that is my molecule. So I'm going to put that there. There it is. D. Butanoic acid can also react with ethanol in the presence of a suitable catalyst to produce an ester. True. The molar mass of ester produced is this. Okay, calculate the atom economy for this reaction. Easy. So let's look at the reaction. So we have a butanoic acid. So let's write it down. So we have butanoic acid. So when we have an acid and an alcohol, so in this case plus ethanol, what it's going to happen is it's basically going to react and it's going to basically form a water molecule. We know it's going to form water molecule and hence produce that ester group. That is the law, basically. Remember, so when you have like a, let's say, we have a double, this is the, in this case, let's say this is the acid and you have the alcohol. What's going to happen, these are going to form. And so you basically get an ester group. That's what's happening here. There it is. And that looks good. So butanoic acid and ethanol and water and ester group. So remember your atom economy is what? Remember the formula? It's in your formula sheet. Basically, what it is, it's basically what's the molar mass of your desired molecule? Well, we're looking at the ester group. So what's the molar mass of it? Did they give it to us? Yes, they did. Yep. So 116. And we need to find the molar mass of the overall reactant. So butanoic acid and ethanol. So butanoic acid, what is it? So butanoic, so CCC, COH. That's what it is. So it's basically how many carbons? We have 4 carbons. How many hydrogens? We have 3, 4, 5, 6, 7, 8. We have 8. Oxygens, we have 2. Plus, what about the ethanol? Ethanol, let's have a sketch of that. CC, OH. That's what it looks like. So it has C, 2 carbons. How many hydrogens? 3, 4, 5, 6, 6. 1 oxygen. So adding basically the molecular formula, like the overall, we have overall 6 carbons, so 6 times 12, plus we have 14 hydrogens, plus we have 3 oxygens. Basically, we get 1, 3, 4, and we times that by 100 to make it a percentage. So that gives me 116. That gives me basically how many? So to afford significant figures from that, it gives me 86.57%. Done. Nice. Let's just cut this. Beautiful. Next question. Question 5. Hydrogen gas can be produced by reacting methane with steam. So, okay, H2O at 300 degrees Celsius in the presence of a suitable catalyst. The equation for the reaction is shown below. Beautiful. So it's a positive enthalpy change. We'll state a source of methane. Beautiful. There's so many ways we can actually get methane. We can get it from biogas. We can get it from natural gas, which is basically the same as coal seam gas. You can get it from so many things. Now, yeah. So I'm just going to say natural gas. Natural gas. There's many ways you can form methane. A suitable catalyst plus 25 moles of CH4, 25 moles of water are placed in an empty container and basically in a 100-liter container at 300 degrees Celsius. After the reaction has reached equilibrium, the container has basically contained 6.12 moles of hydrogen. All right, beautiful. Write an expression for the equilibrium constant. Done. So equilibrium constant is the product, so H2 to the power 4, CO2, H2O squared, CH4. Calculate equilibrium constant K for this reaction. We need to use the ice table because remember, these values here are basically initially placed. They are actually not at equilibrium, those moles. So let's write the reaction. So CH4 plus 2 H2O, CO2 plus 4H2. Beautiful. So we're going to write ICE, so ice table. So what is our initial molar mass? So mole of CH4. They told us that it was 25. How many moles of H2? We had also 25. And of course we would have, because they were initially put, there would have been no forms of H2 and CO2 initially. Now the change, now we're going to have a loss in these reactants. So negative X for this one, because we're going to lose, it's in a reactant, and it's going to, there's a coefficient of 1. And this one is also going to be lost, but it's going to be 2 times. So negative 2x. This is now going to form, these are your products, and it's going to be plus x here, and this one here, 4x, so plus 4x, because there's 4 of them. And now at equilibrium, what's the molar mass? We know the molar mass of H2 is 6.12. 6.12. So we can actually, basically, this is what the rule is. If you add the ice and the change, you get the equilibrium. So 0 plus 4x, which is basically just 4x, equals 6.12. Hence, x is what? 1.53. Beautiful. So because we got x, we can actually calculate the other ones. So 0 plus x, we get our equilibrium value. So which is basically 0 plus x is x, which is just 1.53. Doing the same for this one. So what's 25 minus 2 times your x? So 25 minus 2 times that. You get 21.94. And what about the other one? So 25 minus x, which is 1.53. $23.47. Done. Those are our equilibrium values for our mole. But remember, we want them in concentration. So to do that, it's very easy. So concentration ones. All you need to do, remember, concentration is the mole that we've just got over the volume. The volume is just constant 100. So what's this divided by 100? That should give us our... divided by 100, we get, so let me write it like a different color. Basically that's 0.2347. The next one, 21.94 over 100. Basically 0.2194. Next one, 1.33 divided by 100, 0.0153. Last one, 6.12 divided by 100, 0.0612. Done. So now putting it in our K value, so K formula. So K is what? So it's the hydrogen concentration, which we got is this. So 0.0612 to the power 4 times your concentration of CO2, which is 0.0153. all over the water concentration squared, so 21.94 squared, times your CH4, which is 23.47. That's going to give me what? Times 0.0153, 21.94 squared. 23.47. So 23.47, and we get basically to how many significant figures? 3. So 1.90. Have I done anything wrong? 1.90 times 10 to the negative 11. That is very, very small. Any mistakes have we made? Have we made any? Let's think. Have I subbed it wrong? Let me try to sub them in again. So let me check. Nope. My apologies. Big problem for me. I did this wrong. These here, it's supposed to be subbed in 0. So which is, your H2O2, which is 0.2194. And this one here is 0.2347. I didn't sub the concentrations, I subbed them moles. So now doing that again. 0.0612 to the power 4. Is that right? So 0.0612 to the power 4 times 0.0153. So 0.0153 times 0.2194 squared times 0.2347. So 0.2347 done. Enter. Then we get a nice answer. So we get basically again 1.9. So 1.90 times 10 to the power of 1, 2, 3, 4, 5. Then a negative 5. And what's the unit? Remember, there's actually a quick trick before even doing maths and stuff. What you just need to do is look at the product. How many moles are there? So we have 1 mole from the CO2 and we have 4 moles for the H2O, hydrogen gas. So that is overall 5 moles. Do the same for here. So we have 1 mole from here. We have 2 from the water. So overall 3. And always product minus your reactants, which is 2. So 5 minus 3, which is 2. And so it's going to be m to the power of 2. That is the trick. M to the power 2. That is done. Beautiful. This is the last question. Yeah. Okay. The temperature of the equilibrium system is decreased. So the temperature is decreased. State how the decrease in temperature changes the shape of a Max-Boltzmann distribution. You may use a diagram in your answer. Easy. Let's have a draw at a Max-Boltzmann diagram. So basically the Max-Boltzmann diagram has energy, so energy, and the number of particles. So basically what it looks like a kind of a normal distribution graph like that. Like a nice, like that. Say this is your activation energy. So this is here, your activation energy. So by the way, the area under a Max-Boltzmann graph is the number of particles. So for example, here, the ones that are here, the area under here, it means these are the number of particles that have gone over and beyond. They have the energy that is greater than the activation energy and hence are reacting. Whereas these ones here don't have enough energy to overcome the activation energy. Now, when we're decreasing temperature, what's happening? We're decreasing the kinetic energy of those molecules. Remember, you're decreasing the energy molecules and hence less are going to be able to overcome the activation energy. So, but you remember, so what it's going to look like, it's going to look like this. It's going to be like one that's going to look like it's going to have a higher peak and it's going to go like this. Have a look at this now. The activation energy is here, but look at the difference now, the area under there. It's only less now. You can see that there's only less number of molecules that are able to go above and beyond because of the kinetic energy has been decreased. And remember, can you see how wide did this go up in terms of peak? It's because remember in the Max-Boltzmann graph, it's a constant number of particles. So if this is the area of the particles in the blue graph, there have to be the same number of particles in the, green graph. So that's why it kind of picks up. And that's what it looks like. Beautiful. So how does it look like? So it changes shape. What it basically looks like is basically, you know, the peak here. So originally it was here. Now it's basically shaped to the left. So it's now, you know, on the left. It's like shifted to the left. And you can see that the width here was larger, whereas the width here, it becomes smaller. So that's the changes that I see. So we're going to write those. So the peak of the curve shifts to the left, and the width becomes smaller. And that is it for 1 mark. Yeah, I hope you guys enjoyed this video and learned something for this video. Please make sure to like and subscribe for more future videos like this, and I hope you guys have a great day. Bye bye.